Right, now we talk about from the transfer function h of s, we can convert it to something very useful called the frequency response h of j omega. You may remember h of j omega or h of omega from the continuous time Fourier transform. This is the same h omega, except that in the s domain, we are replacing s equals to sigma plus j omega, and we are setting sigma equals to 0. That's all, so that we'll get just s equals to j omega. Now, when s is just evaluated along the imaginary axis j omega, it becomes exactly the same as the frequency response of the continuous time Fourier transform of the impulse response. Let's see. Okay, let's begin with this idea. So this input signal is the everlasting complex exponential, est, and s is a complex number, so maybe it's e sigma plus j omega t. And once you have a j omega t, something the complex exponential is actually rotating. So, and not only that, we are specifying that this signal exists for all time. Alright, when this signal is being sent into a linear time invariant system with impulse response h of t, we get y of t. And then when we have applied this, we can then apply the convolution equation. The convolution equation is nothing but the integral of the impulse response called h of tau. So now the dummy variable is tau, and the input is e s t minus tau for all tau to get only one t. So we are, this is a convolution equation, and to get a single time, we are integrating through all of tau. Now, what you realize is that we can break this equation up. We can break this equation into est times es tau minus. Okay, so there's a minus sign missing here, should be minus s tau. And what we then get is, isn't this exactly the Laplace transform of h tau? So it's equals to h of s. Now, what is this? est, wasn't this exactly the input? Yes, it is. So the convolution equation simply reveals that the convolution reveals that we get the input signal back, as well as it being multiplied by hs tau, h of s. Now, what is h of s? We saw in the last slide, h of s is the transfer function. So, this very nice thing happened for est as input. When est is being sent into an LTI system, out come est. It is signal with this property is called an eigenfunction. This eigenfunction is being modified by h of s. This guy is a complex number, and this complex number will represent a change of magnitude as well as a phase shift on the signal est. Okay, so what you realize is that we can now study est for different value of s with a lot of details. We would know what's happening to est as it passes through the LTI system, whether it becomes bigger or smaller, so that's the magnitude, and whether it's shifted in phase or not. Just like a cosine, it will shift a few degrees to the right or the left. Now, when we let s equals to j omega, something more interesting also happened. We now change h of s to h of j omega, because we substitute s equals to j omega, we set sigma equals to 0. So this we set to 0. Now, what happened is, now we are not studying a general EST anymore. So we are not looking at EST. We are looking out at EJ omega naught t. When we look at EJ omega naught t, this, remember, is a continuous time complex exponential rotating at omega naught. It does not decay. It does not grow. It remains with an amplitude of 1, and it keeps on rotating at omega naught radian per second. That's the idea. So this is a forever, everlasting complex exponential with analog frequency omega naught. And this is being sent into a LTI system with this impulse response. Now, again, when we deal with this, EJ omega naught is being sent to, what happens? Well, frequency response will tell us how the signal will change. So here we have EJ omega naught t. It is being modified by its some magnitude. So the EJ omega naught will change, will become bigger or smaller depending on this value here, as well as it will shift by phase. Angle here, but angle is given by the angle of Hj omega naught. So the cool idea is, once we have found Hs, we just dump in J omega naught, and we can now find how a complex exponential will behave as it passes through the LTI system. Now, some of y'all don't like to deal with complex exponential, so let's deal with a cosine. A cosine is nothing but sum of two complex exponential anyway. So its behavior will be very similar, and in fact it's true. A cosine of amplitude 1 will have its amplitude modified by Hj omega naught. So what we do is we substitute Hj omega naught. Hj omega naught will be a complex number. So we take the magnitude of it to get the magnitude response. So this guy is called the frequency response. You have the frequency response have two components, the magnitude and the phase. So this is computing the magnitude, and this guy is computing the phase. So the cosine, the one cosine omega naught t, will now have its magnitude change, as well as you have a phase shifted by this angle Hj omega naught. Okay, so the purpose of frequency response inform us how a complex exponential will have its magnitude and phase change as it passes through. Alright, some explanations given here. Please read. Now, the take-home message may be this. It looks very nice to use, but this result is only valid when the system H of S, when S equals to J omega, is exists. It is converging. Okay, so you look at the pole, and the pole must sit on the left plane such that the J omega axis is in the region of convergence. Right, we go to the next slide. Maybe some more terminology. This frequency response actually tell us the steady state response of the complex exponential. That means as we calculated the magnitude and the phase response, we are assuming that the cosine or the complex exponential has been sent in for a long time, such that all transient dies. Okay, so this is called the steady state response of the sinusoid. In the next few slides, I will show you what a transient response does. Alright, so some other terminology. So maybe I collect all the terminology and I put it in this table here. So let's try it again. H of t, this guy, is called the impulse response of the LTI system. H of s is called the transfer function. H of j omega is called the frequency response. The magnitude response is that with the 2 little bar, it is nothing but taking the absolute value of the Hj omega and this is taking the phase angle of the Hj omega. Okay, and remember, to go from the transfer function to the frequency response, all we need to do is to set S equals to J omega. Now, when we get, let's say A e j omega t plus phi is our input. So the input is no more 1 e j omega t. It is A e j omega, well, whatever omega this is, for example, omega naught. Then what happens is that what we do is we will take this omega naught, the frequency that that is of the input, and we will substitute this as j omega naught into the frequency response to get a complex number. We take the magnitude of this and put it here. So A remains, the A is from here. This is how the complex exponential will be changed as it passes through the LTI system in the Y. Okay, and then of course we also take the angle here. So the complex exponential original omega naught is here. The original phase is here. Okay, but now we have introduced a new phase. So this is why we have a magnitude change and a phase change in the output. All right. In the next few slides, we'll see more examples. Thank you.